The active geology of Ceres is driven by ice and brines. Water leached from rock is estimated to possess a salinity of around 5%. Altogether, Ceres is approximately 50% water by volume, compared to 0.1% for Earth, and 73% rock by mass. Ceres' largest craters are several kilometers deep, inconsistent with an ice-rich shallow subsurface. The fact that the surface has preserved craters almost 300 kilometers, 200 miles, in diameter indicates that the outermost layer of Ceres is roughly 1,000 times stronger than water. Ice. This is consistent with a mixture of silicates, hydrated salts and methane clathrates, with no more than 30% water ice by volume. Gravity measurements from dawn have generated three competing models for Ceres' interior. In the three-layer model, Ceres is thought to consist of an outer 40 kilometers, 25 miles, thick crust of ice, salts and hydrated minerals, and an inner muddy mantle of hydrated rock, such as clays, separated by a 60 kilometers, 37 miles, layer of a muddy mixture of brine and rock. It is not possible to tell if Ceres' deep interior contains liquid or a core of dense material, rich in metal, but the low central density suggests it may retain about 10% porosity. One study estimated the densities of the core and mantle crust to be 2.46 to 2.90 and 1.68 to 1.95 grams per cc respectively, with the mantle and crust together being 70 to 190 kilometers, 40 to 120 miles, thick. Only partial dehydration, expulsion of ice, from the core is expected, though the high density of the mantle relative to water ice reflects its enrichment in silicates and salts. That is, the core, if it exists. The mantle and crust all consist of rock and ice, though in different ratios. Ceres' mineral composition can be determined indirectly only for its outer 100 kilometers, 60 miles. The solid outer crust, 40 kilometers, 25 miles, thick, is a mixture of ice, salts, and hydrated minerals. Under that is a layer that may contain a small amount of brine. This extends to a depth of at least the 100 kilometers, 60 miles, limit of detection. Under that is thought to be a mantle dominated by hydrated rocks such as clays. In one two-layer model, Ceres consists of a core of chondrules and a mantle of mixed ice and micron-sized solid particulates, mud. Sublimation of ice at the surface would leave a deposit of hydrated particulates perhaps 20 meters thick. The range of the extent of differentiation is consistent with the data from a large 360 kilometers, 220 miles, core of 75% chondrules and 25% particulates and a mantle of 75% ice and 25% particulates, to a small 85 kilometers, 55 miles, core consisting nearly entirely of particulates and a mantle of 30% ice and 70% particulates. With a large core, the core-mantle boundary should be warm enough for pockets of brine. With a small core, the mantle should remain liquid below 110 kilometers, 68 miles. In the latter case, a 2% freezing of the liquid reservoir would compress the liquid enough to force some to the surface, producing cryovolcanism. A second two-layer model suggests a partial differentiation of Ceres into a volatile-rich crust and a denser mantle of hydrated silicates. A range of densities for the crust and mantle can be calculated from the types of meteorite thought to have impacted Ceres. With C-class meteorites, density 2.46 grams per cc, the crust would be approximately 70 kilometers, 40 miles, thick and have a density of 1.68 grams per cc. With CM-class meteorites, density 9 grams per cc. The crust would be approximately 190 kilometers, 120 miles, thick and have a density of 1.9 grams per cc. Best fit modeling yields a crust approximately 40 kilometers, 25 miles, thick with a density of approximately 1.25 grams per cc, and a mantle core density of approximately 2.4 grams per cc.